This video is going to be slightly different than the past few, but I hope it is a really special video as well. And this video we're going to go into a program that I have made, and we're going to explore the Mandelbrot set in its most glorious form. And the first thing you probably notice, okay, so you would recognize the general shape of the black area. The first thing you would notice is that, well, there's color. And if you remember the algorithm that we had, where we set up, if I here I'll go back to smooth draw here. If you remember the algorithm we had, where we started with z of 0 equals a plus bi, this is a complex number. The algorithm where we went, alright, well, z1 is going to be z0 squared plus z0, z2 is going to be z1 squared plus z0, z3, this is going to be, well, z2 squared plus z0. This algorithm that we had, where at every point we said z of n plus 1 is, so the next z is the previous z squared plus the first complex number. This algorithm that we had, this was here giving us a way of saying, okay, if as these z values, as the list goes on, if this diverges, if this goes far enough away from the origin such there will be no return, then the point is not in the Mandelbrot set. But if the point kind of just spirals around and, hangs around the center forever, then it is in the Mandelbrot set. And the way that you do this programmatically, let's get ourselves even some more room here. The way that you do this programmatically is you don't do an infinite number of iterations as you would in the best mathematical, in the pure mathematical case. You do a finite number of iterations. Let's say you do this up to z100, and you say, has z100 exceeded a magnitude of 4? Magnitude of 2. Is the magnitude of z100 more than 2? If so, then the point you say is not in the set. It's been proven that 2 is an escape radius. If the magnitude is ever greater than 2, the point will escape. So you have, if it's greater than 2, then the point is not in the set. And you do this 100 times, say some discrete number of times, and you do that at, say, this point, and it's not in the set. And you do it at then this point, and this point, and this point, and you do it at all of the pixels on your screen, calculating if that pixel's in the Mandelbrot set. And when you're done, you get something like this. This is just my bad rendition of it, but you get some area of pixels that don't get colored in, and this area here would be your Mandelbrot set. How is it colored? That was the original question. How is it colored? Well, it's colored by saying, alright, some points are going to not diverge. Those are the ones in the set. Of the ones that do diverge, how quickly do they diverge, right? If you have a point way out here, it will very possibly diverge on the first step. It'll very possibly just go away incredibly quickly. Whereas if you have a point that is very near, to the edge here, this edge is where the Mandelbrot set lives. It's where the points that don't diverge are. If you have a point very near to this edge, it's very possible that this point would hover around the origin for a long time. After all, it's not too different from points that never leave the origin, but eventually move away. And you can color these points very close to the set that stay in the origin for longer. You can color these points differently than those that take longer to diverge. So that's just a quick intuition on how I'm coloring them. And if you wanted to zoom in, you would of course just be calculating this Mandelbrot set on a different set of complex numbers, a zoomed in set. And let's go back here to this. So right here, as you can see, we have the set, and it's just changing color. That's not a feature of the set itself. That's just how I programmed it to make it visually interesting. So let's just explore. Let's try some points. Let's see. We can zoom into this part. Just clicking here to zoom in. You see it stays snaky. It stays interesting even as you go on and you zoom in here. And so if we just continue zooming in here, you see it's incredible. It is. And I'm gonna make my program. It's saving computation here by not drawing everything, but I'm gonna make it do every pixel here. So just press my keyboard, and you can see it is this incredible, swirly, magical combination of, I don't know what to call it, but you see this it just looks incredible. Lost for words here with the Mandelbrot set. And if we were to zoom in on part of it, say this part, we're zooming in, you see it's just it's incredible. Here there's a little Mandelbrot set right in here where I'm clicking now, where my mouse is. If we zoom in on that, we're going to get closer to it, and we'll see it. You'll see all of these copies of the Mandelbrot set. They're everywhere in the set. You see little Mandelbrot sets everywhere in the Mandelbrot set. That's one of the signs of a fractal, is these little Mandelbrot sets. And if it seems like your computer's lagging, it's just that it's having some trouble drawing every pixel at once. It's quite computationally intensive. There actually is quite a bit of work that's been done in trying to make this a faster process. Here I'll give us a little bit less precision in exchange for higher speed here. So we can click, you see all these little Mandelbrot sets. These little Mandelbrot sets that are just the same as the big one, except they are way smaller. And you see the black being carved away. That's because I'm pressing my up arrow key. I've programmed it in so that increases number of iterations. So as you go smaller, if you're only performing, say, 10 iterations, you're going to miss some of the points that were actually not in the Mandelbrot set that you think might be. So when I press the up arrow key, it tells the computer, run, maybe instead of 100 iterations, run 200, run 300 iterations to see if the points are diverging. Because if you don't, it's possible that these points will be drawn as if they're in the Mandelbrot set when they're truly not being. So let's just, for the fun of it, let's tell the computer one more time, render this at pixel for pixel precision. This should be quite amazing. The tab is unresponsive. Alright, much better. Sorry about that. I've got the Mandelbrot set back here, as you can see, and let's just, for the fun of it, let's make ourselves have a low resolution so we can zoom in to an interesting part of the set here. And what you see, by the way, with this black expanding and decreasing as we went over before, that's me increasing the number of iterations the computer is doing before it rules out a point, or before it says a point is in the set. So let's just have a look at this here. Pretty incredible even at this resolution. You can see some swirly stuff happening. Let's just get down to that 1 pixel per pixel resolution. Let's bask in the beauty of the Mandelbrot set. That is incredible mathematics right there. Really, really quite beautiful. That is incredible. Well, I hope that I'm leaving you having instilled a sense of awe, at least at what this really, arguably, this is a simple formula. Zn plus 1 equals Zn squared plus Z0. That it can create such extraordinary figures by just plugging numbers in and calculating them. Well, I will see you in the next video.